To start Unit 4, we're going to identify and classify triangles by their sides and angles. And you should already know all of this. Let's make sure you do. All right, to classify by angles. Recall that a triangle is a three-sided polygon. Triangle ABC, written with the little triangle symbol, and then ABC, has parts that are used, or that are named using A, B, and C. So A, B, and C are the vertices. They're the points where the angles connect, or where the sides connect to make the angles. So A, B, and C are the vertices. So the sides then are the segments. So segment AB, segment BC, and segment AC. And remember, you can call segment AB segment BA, same exact thing. And then the angles, if we can get away with angle A, angle B, angle C, then that's what we'll do. If we have to use the three-letter method, then we will. Angle BAC, angle ABC, angle BCA, and so forth. Okay? So far, so good? All right, now, we can classify triangles two ways, by their angles or by their sides. All triangles have at least two acute angles. And later on, we'll learn some facts about triangles that will prove mathematically why that has to happen. But I mean, think about it. If you're going to take three segments and connect them together, I mean, go home and try it out if you don't believe them. Okay? Any way you do it, where the three endpoints, or where the endpoints of each of the three segments connect, two of those three angles are going to be acute. And the third angle is either going to be an acute angle, a right angle, or an obtuse angle. That's the only way it works. Okay? So the third angle then is the one we use to classify the triangles by its angles. No matter what, there's going to be at least two acute ones. If the third angle is an acute angle, it's called an acute triangle. If the third angle is an obtuse angle, it's called an obtuse triangle. If the third angle is a right angle, it's called a right triangle. And then we have a special kind of acute triangle called equiangular. If all three of those angles are congruent, they're all acute, and they're all congruent, it's equiangular. So equiangular is a subset of acute. With me? All right. Let's do some from your assignment. So let's see. This would be on page 238. We're going to classify each triangle as acute, equiangular, obtuse, or right. So number one here, I see a 30 degrees, a 60 degrees, and a 90 degrees. So this triangle would be a right triangle. All right, what's number two? Obtuse. And number three? All right, so not the most difficult thing you've ever done, correct? All right, good. Now, we can make things a little more complicated by putting more things into our figure. So that's what they're doing here. What you've got to do on these is you've got to look at the correct triangle. So number 4, we need to classify triangle ABD. So make sure you're looking at the triangle with vertices A, B, and D. So what's number 4? Then number 5 is triangle BDC. So find the triangle with B, D, and C as your vertices. So what's number 5? And then number 6 is triangle ABC. So A, B, and C is the vertices. I don't see a right angle mark. But 60 plus 30 is 90. That's a right angle. So that's about as much trickeration as they're going to give you. That's a word. I just made it up. All right. We can also classify by sides. So triangles can also be classified according to the number of congruent sides they have. And you can have none, or you can have two. You can't have one congruent side, right? So you can have 0, 2, or 3 congruent sides. So to indicate that sides of triangle are congruent, an equal number of hash marks is drawn on the corresponding sides. We knew that, right? We've marked congruent segments before. So an equilateral triangle has 3 congruent sides. An isosceles triangle has at least 2. Now, think about that. At least 2. Is 3 at least 2? Yes. So technically speaking, an equilateral triangle is a subset of isosceles triangles. Okay? That becomes important later on down the road when we learn some theorems about isosceles triangles. Everything we learn about an isosceles triangle will also apply to an equilateral triangle, because an equilateral triangle is simply a special kind of isosceles triangle. Now, having said that, when you're asked to classify, to be clear though, when you're classifying triangles, if it's equilateral, call it equilateral. Don't call it isosceles, because equilateral is a better description, isn't it? So give the most specific description that you can. So technically speaking, equilateral is a type of isosceles. But when you're classifying, if it is equilateral, call it that, because that's a more specific label than isosceles is. Okay? Just like with the equiangular instead of acute, equiangular was a type of acute, but equiangular is more specific than acute, so that's what we used when we classify. By the way, we've got 2 things with equiangular and equilateral. We can probably guess that equiangular equal angles. Equilateral, what's up with that? What's lateral? Sides. Think sides. Okay? So you got equilateral, isosceles, and if there are no congruent sides, then it's scalene. All right, so number 7. What is it? It's isosceles, and be able to spell isosceles. What's 8? Scalene. All right, let's see here. If K is the midpoint of segment FH, so I'm going to mark something on here. If K is the midpoint of segment FH, then those 2 segments, KF and KH, are congruent to each other, aren't they? Okay? Now classify as equilateral, isosceles, or scalene. So triangle FGH. So use F, G, and H as your sides, or as your vertices. All right, now let's do some thinking here. If FG is congruent to GH, and FG is 5, what's the length of GH? 5. If KF and KH are congruent to each other, and KH is 2.5, what's KF? 2.5. So what's HF? 5. What kind of triangle is it? Yep, so number 9 is equilateral. They made us work for it. All right, number 10, triangle GJL. So G, J, and L are the vertices. Now remember, GH was 5. So do we have any congruent sides here? Yeah, which 2? GJ and GL are both 8, aren't they? So what do we have? And then for number 11, F, H, and L are the vertices. And what do we have? Scalene, because FH is 5, HL is 3, FL is 7, no congruent sides, scaling. Let's keep going. Number 12. It says find x and the measure of the unknown sides of each triangle. All right, let's see here. For number 12, we have segment LN marked as congruent to segment MN. So if the segments are congruent, the lengths of the segments, the measures of the segments are equal. So 3x minus 4 equals 2x plus 7. And then you solve it for x. Subtract 2x from both sides. You'll get x minus 4 equals 7. So x equals 11. Then it says to find the measures of the unknown sides. Now we know the measure of LM is 17. They give us that. We need to find the measure of MN and LN. And by the way, MN and LN have to have the same measure, don't they? Since they're congruent. All right, so MN is 2x plus 7. So that's 2 times 11 plus 7. That's 22 plus 7. What's 22 plus 7? 29. Now, without writing it down, you might just want to mentally do this. Do you get 29 when you put 11 in there? You do, don't you? 33 minus 4. So not only is MN 29, LN is also 29. And we're positive because we double checked it. All right? On 13, we have 3 different segments marked congruent to each other. Do not, I repeat, do not do this. Because although that's true, I don't know how to solve that. So what do? That's also true, isn't it? I do know how to solve that. Now, did it matter which 2 sides I picked out to use? No. So all you got to do is take 2 of your congruent sides and set their measures equal. And let's see, that'd be 2x equals 10, x equals 5. So what's the length of every side? It's 25, right? I looked right there first. 5 times 5, 25. That one would be 30 minus 5, 25. That one would be 15 plus 10, 25. So you can write it this way if you want. The book will do this quite often. They'll do the length of QR equals the length of RS equals the length of QS equals 25. You can do that. I'm not a huge fan of it, but everybody else seems to be. Okay? All right. Still doing okay? Last one we're going to do together. Suppose you are bending stainless steel wire to make the earring shown. The triangular portion of the earring is an isosceles triangle. See? 3.2, 3.2. If 1.5 centimeters are needed to make the hook portion of the earring, so that is 1.5 centimeters, how many earrings can be made from 45 centimeters of wire? Well, how many centimeters of wire are required to make 1 earring? Is it 10? 1.5 plus 3.2 plus 3.2 plus 2.1? Okay, so if it takes 10 centimeters of wire to equal 1 ear ring. All right, and how many centimeters do we have? 45. So how do they word this? Where's the question? How many, okay, earrings. I was afraid they were trying to trick us with pairs of earrings. How many earrings can we make? 4. And we're not going to bother making a half an earring, right? Okay. So we can make 4 earrings with 5 centimeters of wire left over. And I think that ought to do it. Questions? All right. On page 238, let's do 1 through 14, 15 through 35 odd, 36, 37, 41, 43, 45, 49, 51, 65 through 68. That sounds like a lot because it is.